start today's class. So today at first we are going to know about what is exact equation and we are going to see some examples. So if the differential equation m dx plus n dy equal to 0 where m and n are functions of x and y is expressible in the form du equal to 0 without multiplying by any factor where u is a function of x and y, then it is said to be an exact differential equation. So if the equation m dx plus n dy equal to 0 is exact, then the general solution of the equation is clearly u of x comma y equal to c, where c is an arbitrary constant. Now for example, the equation y dx plus x dy equal to 0 is an exact differential equation since y dx plus x dy equal to d of xy. Its general solution or primitive solution is xy equal to c. The equation 2x square y dx plus 2y square x dy is an exact differential equation since this is equal to d of x square y square. Its general solution is x square y square equal to c. Now we are going to prove this theorem. So let the equation m dx plus n dy equal to 0 be exact. Then what will happen? Yes, there exists a function u of x comma y such that m dx plus n dy equal to du, where u is a function of x and y. But what we know? We know that du equal to del u del x dx plus del u del y dy. Now equations 1 and 2 must be identical. Then capital M equal to del u del x and capital N equal to del u del y. This implies del m del y equal to del 2u del y del x and del n del x equal to del 2u del x del y. Now, by assuming the continuity of second order partial derivatives of u, we have del m del y equal to del n del x because del 2u del y del x equal to del 2u del x del y. Thus the condition is yes, necessary. Now we are going to prove that the condition is sufficient also. So for that we are going to assume that let the condition del m del y equal to del n del x holds. Now let capital F equal to integration m dx when y equal to constant. Then del f del x equal to capital M. So del 2f del y del x equal to del 2f del x del y equal to del m del y, and by this we can write equal to del n del x. Then del x of n minus del f del y equal to 0. This implies n minus del f del y is constant as far x is constant, that is a function of y, say phi of y. So capital N equal to phi of y plus del f del y. Now let us choose a function u of x comma y such that u equal to f plus integration phi of y dy. So del u del y equal to del f del y plus phi of y equal to capital N, and del f del x equal to capital N, that is del u del x equal to capital M. So m dx plus m dy equal to 0 implies, instead of m we are going to write del u del x dx plus del u del y dy equal to du. So the equation m dx plus n dy equal to 0 is exact, and hence the condition is sufficient. Now we are going to solve this numerical. So here m equal to x square minus y and n equal to y square minus x. So del m del y equal to minus 1 equal to del n del x. Thus, the equation is exact. Now, integration m dx when y equal to constant equal to integration y equal to constant x square minus y dx equal to x cube by 3 minus xy, and n dy when x equal to constant equal to integration x equal to constant y square minus x dy equal to y cube by 3 minus xy. So since this term is repeated, it will be counted for once. Thus, its general solution is 1 by 3 x cube plus y cube minus xy equal to c. Now we are going to solve this equation. So here capital M equal to y square e to the power xy square plus 4x cube and n equal to 2xy e to the power xy square minus 3y square. So del M del y equal to 2y e to the power xy square plus 2x y cube e to the power xy square and del n del x equal to 2y e to the power xy square plus 2x y cube e to the power xy square. Thus del m del y equal to del n del x. Thus the equation is exact. Now integration m dx when y equal to constant is equal to integration y equal to constant y square e to the power xy square plus 4x cube dx equal to y square e to the power xy square by y square plus 4x to the power 4 by 4 equal to e to the power xy square plus x to the power 4 and n dy when x equal to constant is equal to integration x equal to constant 2xy e to the power xy square minus 3y square dy equal to e to the power xy square d of xy square minus 3y cube by 3 equal to e to the power xy square minus y cube. So, the general solution is e to the power xy square. It will be counted once because it is repeated plus x to the power 4 minus y cube equal to c. You can write here where c is an arbitrary constant. So that's it for today. We are going to meet in the next class. Till then, bye.